Hello guys, it's Sebastian Seun. Today I'm going to be going over chapter 25 and 26 in this part 1 video, and part 2 I'm going to be posting tomorrow morning. And let's just begin with the topics that we have on our midterm this time. So with chapter 25 and chapter 26 is what I'm covering. So in chapter 25 we have concepts of current, resistivity, resistivity, resistance, electromotive force, circuits, um, energy and power. And when I say circuits in this context, it is the most basic version of a circuit. So let's start with what is current. So current is the flow of electrons, aka the flow of charge. So current is the flow of charge, and most of the time it is in a wire. But the true definition of current is equal to the change in charge over the change in time, or the instantaneous or the calculus version is dq over dt, which genuinely they're the same thing. Um, you can also define it as delta q is equal to the sign charge times the electron density by the area, by the cross-sectional area times L over the delta T, which is equal to L over drift velocity. And this makes sense because length over the distance of drift velocity over the amount of charge just randomly moving through a material makes sense. And for Q, Q is like what's the charge? This helps you give direction. So the charge density. So this is charge density. This is our area, and then this is also our length. And when we look at the complete formula for what drift velocity is, which is drift velocity is equal to I over uh, I over NEA. This makes sense now because E in this case is the charge. It's let's just change E to Q for this scenario. And then if we just do the quick algebra, what's I? I is let's rearrange that uh so VDNQA is equal to I. And then if we put that equation together, which I is also equal to, which is also equal to delta Q over delta T. So uh, delta U is QNAL over L divided by VD. VD goes on top because math. L's cancel. All of this goes away. And now you got QNAVD. Drift velocity is equal to I, which goes back to our original equation. Remember, drift velocity, I'm going to make this red. Drift velocity is always opposite of flowing current. flowing current. So we checked off the definition of current, what is current so far, and we've also went over drift velocity. So now let's talk about what current density is because we have this equation on ours. So let me go back to my favorite green color. So current density is written on our equation sheet as J as a vector is equal to Qn drift velocity d. And for this also helps to define what our current is because apparently current is equal to the integral of our current density over our area, which, well, if you think about it, that makes sense because our current density, if this is our current density, and we go on to our graph chart, let's say this is um, uh, amps over its area, so meters squared, and this is meters. If you take our little chart, the area underneath this is going to be whatever our amps is. So this would be amps. Amps down here, which explains the integral in nice, easy fashion. Um, That's just a little quick visualization. That's how I always think about integrals, and it helps, especially when you get so far down the calculus line, you forget the basic definition. It helps come back and brings you back to reality. And when you're doing these massive problems, sometimes you just need some simplification. Okay, Ohm's law. So, the direct definition of Ohm's law is that Ohm's law is the in electrostatic equilibrium, the electric field or inside of conductors are zero. If there is a current, then the conductor is not an equipotential current. It is driven by a potential gradient, aka E is not zero. The electric field inside of the wire is not zero in the conductor. And thus, the potential gradient can be established by applying potential voltage difference across the conductor. With a battery, if I is equal to the integral of current density by dA empirically, then V is equal to IR, where R is the resistance of the conductor, and ohms and 1 ohm is equal to 1 volt over 1 amp, which is and conductance is the inverse of of resistance. So let's break that down into something that's actually usable for this exam. So inside of a conductor, when there's no current, there is no electric field inside of this. No electric field. And as we know, when there's an electric field, particles want to go move through it. Okay? But with no potential lines, no voltage difference between the two sides, so let's say this is 0 volts and this is 0 volts, or even 50 and 50, both of them, because the potential across it's the same, there's no gradient, there will be no electric field lines inside of this. But now we change this to 100 volts. Now there's a electric field within the conductor, which then promotes the flow of electrons. Sorry, I'm a horrible drawer. But now we're saying that the conductor has some push to it. That when you put a voltage across it, it has some resistance. has some resistance to it, which dictates saying, hey, we know we want to get this charge from here to this charge here, but because of the resistance, it's the material, we can't just do it as fast as the speed of light. We're going to have to slow down because the material is blocking us. Makes sense, right? And that's how we started developing Ohm's law, which is V is equal to IR. Okay? And now if we think about it on the graph sense, or in the material sense, it kind of does make sense that if you're taking the voltage over resistance is equal to I, so voltage is the potential between the two, and we can determine the amount of potential difference between point A and point B from point A to point B. Uh, the potential difference between, let's say we did this in a vacuum and we're talking about Coulomb's law again. The potential that will go across this distance of distance d is set because we can calculate this with potential energy converting V into U, and then from U into potential energy, which is 1/2 mv squared, yada yada. Now, now we're saying that now we're ripping that away, and now we have our unit, the ohm. The ohm conceptually is essentially this entire constant, this entire section of this, multiplying it by a factor, or dividing it in this case, dividing it by a factor that would slow it down. Slow it down. And then that's how we get I, because I is Q over T. So I'm not going to do the massive algebra right now. I didn't prepare it. I'll probably post it on my video notes in the morning after all of this is done. Okay? So I give you guys a good note that our professors are not that super great at doing. Don't tell them I said that, or at least the the mine, I'd say. Now, let's talk about Ohm's law in other cases where so local forms of Ohm's law. I'm following one of our professor's slides a little bit to help make sure I cover all the topics. Is that E is equal to R vector by resistivity, current density by resistivity, and these are both functions of R, as it's said right here. So, which essentially means we could just get rid of them. Just keep in mind you're going as a function over R, but for the rest of this purposes, you're not really going to need to think about it. And your your resistivity value is whatever material you have. So let's say we had copper. Our resistivity value is actually how much this material in this certain length has this much force to it. So so our resistivity value can be resistivity value units is an ohm meter. And if we go to our resistance equation for resistivity, which is resistivity L over A, we know, so if we just wrote out the units and wanted to see how they canceled, ohm times meter, ohm meter times a meter over meter squared. So, oh, 1, 2, 3, we get ohms. Merry Christmas. And now, just a quick mental thought. If the resistivity value is really high, what do you think it is? Is it an insulator or a conductor? And the answer, it's an insulator. Because if the resistivity value is high, then then the then it's going to resist a lot. And if it's small, then it's small because it's in the top. That's what I like to do. If it's in the top, and you change it, magic. It follows the same direction. If it's in the bottom, it's inverted. And there's charts on which metals have these types of resistivities, and we could talk about that, but you're not going to have to memorize it. It's not important. Um, oh, and this is a quick thing from Ohm's law. I did mention it up here that V is equal to, let's assuming voltage, potential difference across. I actually looked on the notes and they actually talk about it very similarly, where voltage is equal to the electric field by the change in length, which, if you think about it, makes sense. And now that we say electric field, field of length, you can go about the algebra how I mentioned it up here with I and current, and just when you break down the units, it becomes it. But now that I've mentioned it, I hope it's in your brain that if we ever get a question which is like prove this, I'm not gonna do the proof out here because it's long and I don't feel like doing it right now, I'll be honest. But it is a now you have a direction, a stepping stone where you're thinking about it. Um, resistors. Resistors is this equation up here. Oh, don't forget about conductivity. Conductivity is just the inverse of 1 over rho, and it's also C, not C. I'm just gonna write conductivity is also R. Um, right? Yeah, that's it. Just remember that simple concept. It will help you. Okay, this is actually another good one, and is also an equation on our test because I looked at the practice test. Very good concept question. The resistivity as a function of temperature is equal to the initial resistivity times 1 plus the the constant of the material times the change in temperature from its neutral state. So, every metal has a different factor, a constant, that incrementally grows based off of the change in temperature. Because when an object gets hotter and hotter, the electrons in it uh, doesn't want to budge. And this is the same concept when we have with superconductors, that our current superconductors today approach these extremely low resistivities when we approach absolute zero, because now our protons are not moving as much. And when our protons aren't vibrating as much, the electron cloud inside of these particles become very evenly dispersed, which allows for perfect motion. But when you get to higher temperatures, temperatures that get extremely hot, these electron clouds are now misaligned. They are not even. And when you have electron clouds that aren't smooth, electrons don't move properly. That's just a little fun fact. You could throw it out of your brain in a second. But all you really have to know, temperature go up, temperature go up, resistivity go up, and vice versa. Um, DC circuits, power supply. Okay, let's talk about our just what's on our circuit diagram quick. So, on our exam for basic circuits, we're going to have resistors. So this is a resistor. Sure. We're also going to have batteries, which are which is like this. This is an ideal battery, so it does not have an internal resistance. I can't write nicely. Um, my handwriting's horrible, but no internal resistance. Then we're also going to have batteries that have internal resistance. So I'm going to draw it in a box. It's not going to show up like this. Or they could just say, they could just make something like that and say it's a real battery. But this is, but what I'm drawing right now is a real battery down here, plus, and then a resistance. This is how a real battery would look like, one that actually has, one that actually does things. So this would be a real battery, has an internal resistance, and then our voltmeter, and then our ammeter. Um, Voltmeter, ammeter. And a lot of times on these exams, they would just give you a massive circuit, and they'll probably just go right on top of, like, let's say we had a circuit like this, and do, and then let's just do, do. They can just be like, okay, and then they'll just draw this. They're just asking you for the voltage across this resistor, which is a lot easier task than you would probably think, because and I'm just going to go over it quickly. Uh, this is so let's break it up into what's in parallel and what's in series. That's chapter 26. I'll go into it more in depth, but just a quick overview: what's in parallel and what's in series. So this this section is in parallel with this section, and which is in parallel with this section. So you know the voltage across all of these sections are equal. And now we can also say that, let's say, I'll actually assign resistance values to this. So let's say this is 4 ohms, and for simplicity's sake, I'm going to say this is 2 ohms and 2 ohms. So, and let's say this is 8 volts, okay? So we know the voltage from this node from the top is 8, and on here's bottom is 0. And because these two resistors are equal, that literally just says that our voltmeter should be reading 4 volts then, because this is directly 1/2 of the circuit. And now, that's just a quick concept thing that if you looked at this, that's how I would solve it. And let's say they said all the resistors are the same for 4 ohms. How I would solve this now is I would combine these two, because it doesn't matter what the difference between those. But the difference between these, and then I would just go about it the same way, finding the voltage across this, which, matter of fact, should still be 4 volts, because it's halfway between equal voltages. Um, and matter of fact, the only way it would be different is 2 ohms up here, and then you just take a fraction. So so this would be the bottom one, the voltage drop would be 6 then, right? I'm not hallucinating. 2 over 3 times 8. That's what it would be. So 16 divided by 3. I don't want to do the math. 5.333. 333 volts would be the drop if this was 2 ohms and 4. And these are just little tricks that conceptually, if you understand that anything in parallel, anything in parallel, uh, pair, I'm don't know how to spell parallel, don't laugh at me. Anything in parallel is anything in parallel is equal voltage, and anything in series, and the symbol for series is a comma, uh, is uh, is equal current. That also will just help you get through your exams, but we're gonna go more into that in part 26, chapter 26. Um, we covered basic circuits, power. This is the fun one. So power. I have the power. I'm insane. Um, du is equal to dq v. And so that is your potential energy is equal to the change in potential energy is equal to the change in charge over voltage. So P is equal to du over dt, which is equal to dq dt v, which is ultimately equal, v is equal to iv. I mean, not v is equal to iv, which is equal to I times v. Because if you remember, what's your what's your charge over t? dq over dt is I. What a magic scenario right there. Which also means that P is equal to IR squared, uh, IR, which is equal to V squared over R. And these are just all variations of using Ohm's law, which is V equals IR, and P is equal to VI. And then you could derive most of your equations from this. And matter of fact, that just knowing that potential energy is charged is VQ makes V times Q is U. Also, just proves all of the points for everything. We've already been through the first midterm, so I do expect basic electrostatics knowledge when I talk about it, but I'm also a dumbass, so I wouldn't even stress about it. Because on this exam, it'll probably, if it shows up, it's going to be in tiny little bits, and maybe it'll help you out, but if you just remember the hard concept, you're fine. Um, the demo light bulb question, which we all did in class, should have done in class, a 100-watt light bulb and a 40-watt light bulb are connected in parallel. Which light bulb would be brighter? And so I'll just do it then, because why the hell not? So, so let's just draw out a circuit. So this is a battery, and this light bulb is a 40 watt, and this one's a 100 watt. I'm gonna draw them like, I'm not gonna do their stupid load symbol. I'm gonna draw how it's supposed to be done, like a diode, because diodes draw current. Light emitting diodes also have a symbol like that, but this class doesn't teach you anything proper. They just say, oh, pretend this is this, but let's just go over it. Let's do it the way they want it. Okay? So, they're in parallel, which means the voltage over the terminals. So, oh yeah, just a quick thing, little trick from the circuits 1, is that whenever you're working in it with a system, always circle the nodes. So this is node A, and then this is node B. And this just helps you determine the rules from before, which is that anything in parallel has equal voltage and anything in series has equal current. So let's look at our top equations up here and determine which one is proper. So we have our voltage, and we know our voltage is set. So this is an arbitrary number that we don't have to figure out. So we can, for simplification purposes, I'm going to do 10. And so we have voltage and we have power. We don't have resistance. But we do know that resistance, a higher resistance, should result in a lower current if the voltage is constant. And we could do it the long way. I'll do it both ways. So with the shorthand equation, I'll do that one first, is P is equal to V squared over R. We know that this should be a watt symbol. I'll go back to red for solving, but P is equal to that. So if we have 100 watts is equal to the voltage, so 10 volts squared over resistance R, which is unknown, R unknown, we want to move it over. So it's going to be 100 watts divided by 100 volt squared, which is going to leave us with 1 ohm. And now let's do it for the 41. So 40 watts over, I rearranged my equation wrong. I'm a kind of dumb today. Oh wait, it's 1 over 1. So I'm just going to go 1 over 1. So 40 watts over 100 volts squared, which is equal to 100 over 40, which is, I don't want to do this, 2.5 ohms. And then this is 1 ohm. So we know that our 100 watt has a lower resistance. And because it has a lower resistance, it would probably have a higher current. And lower resistance, it would have a higher current. And because this one has a higher resistance, it will have a lower current. And for which light bulb burns brighter, a 100 light bulb draws more power, which means it will have more light if they are using the same mechanical principles. Um, and yeah, that pretty much covers chapter 25. Now, let's go to chapter 26. What a fun day it is. I want to sleep. Chapter 26. See, tomorrow I'm cooking, so I'm so happy for that. Resistors in series and parallel. So we've already talked about this. Series and parallel. Kirchhoff's rule. Rule. Electrical measuring instruments. And RC circuits. Wow. Okay. So I didn't draw them in a list because my brain's on autopilot right now. So, resistors in series and parallel. Yes. So resistors, we're going to have to figure out the resistors equivalence in our massive fun circuits. And the two rules is that R series is equal to R1 plus R2 plus R3 dot dot dot. And parallel, R parallel, I don't know why I write it out anymore. R parallel is equal to 1 over 1 over R1 plus 1 over R2 dot dot dot. Okay? And with these two rules for resistors, you can simplify massive systems of resistors as long as there's not another battery inside. Or you could do it between batteries. So I'm going to draw a very, very complicated circuit from the top of my head with just one battery. Okay? So plus, minus, do, do, do. So, do, do. Mm, um, ah, okay, I'm rolling with that. It doesn't matter. Okay, so just for remember what I say about circling your nodes. So I'm going to do that right now. So all of the electrical elements, the resistors. Oh, let's also assume all resistors in this one. All resistors have a 1 ohm of resistance. So let's. I like to circle my nodes. So we have this wire is all conductive and has all of these elements connect to it. That's node 1. Node 2 is still all of these. And even though this diagonal may seem complicated, you just realize you just have two nodes, and this is technically a third node up here. But this node is only connected to two elements, which means this is in series. So now if both of these are 1, now this is 2. This is a 2 ohm resistor. And because all of this is 1 ohm, 1 ohm, 1 ohm, you put them in parallel. So 1 plus 1 plus 1 over each other. So 1 over 1 plus 1 over 1 plus 1 over 1. Flip it again. This is 1/3 of an ohm. Uh, plus is the equivalent resistance for section A. Section B is 2 ohms. So now do it again. So uh, 3 plus 1 over 2 is 3.5. Right? I'm just gonna, I'll just write it out completely. I'll just do everything in parallel at once. 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 2. Add them up. Yeah, 3.5. 1 over 3.5 is equal to your total equivalent resistance. And that is, I don't want to do this. Um, oh wait, yeah, that's it. And the simplification of that would be 1 over 2 over 7 ohms is equal to your REQ then. Over, and then you're done. Uh, Kirchhoff's rule. So Kirchhoff's rule is a fun one. So there's two Kirchhoff's rule. Kirchhoff's rule. And Kirchhoff's rule 1 is your current, your uh, is your current law, and then your voltage law KVL is that. I forgot the acronym. It's too late for this. But this one is that all current that enters a junction exits a junction. Exits. And KVL is all current, a voltage loop. A voltage loop adds to 0. So as you go around the whole loop, it goes to 0. And for these, so the biggest tip I could give you for this, so what's a good color for a problem? Let's do blue. It's that blue time of day. So you do one, do, do. I feel like this was on our test. I think I'm pulling it from our test and not one of our quizzes. 9 volt, 6 volts, 12 volts. Okay, so let's first define our currents. So our current, so let's start at battery 9 volt, because it's to our left, it's the easiest one to deal with. Oh wait, let me just write the resistor values. This is 12. Um, hmm, let's do 8 ohms, 12 ohms, and 12 ohms, and 6 ohms. So let's go about it like this. First step I always do is start at our 9 volt battery and follow the loop to its first junction. And matter of fact, this is our first and only junction where the currents would split up. So that makes life easy because so you're going to have I1 going into I2 and I3. Okay? And now we want to define our loops. So loop 1 is going to be in the clockwise direction. Loop 2 is also going to be in the clockwise direction. So this is loop 1, loop 2. And then our third loop is the big boy outside, is loop 3. Okay? So let's write out loop 1. So loop 1 going up is 9 volts minus, minus 8 ohms times I1, because that's what in our circuit is. Then we're going down, minus I2 at 12 ohms, and because the battery is facing in the same direction, you're minusing 6 volts because it's counter to our current loop. Okay? And you could see this if you take a real life battery, a 9 volt battery, hook it up in the opposite direction with a AAA battery. The voltage of a AAA battery is 1.9 volts, a 9 volt battery is 9, obviously. And then if you try to read the current between them, you'll realize that one battery is actually pushing against the other voltage, and your voltage is going to be 7.9. Is and then as we're going to follow the voltage law, and then this is equal to 0. So this is resistor 1, resistor 2, battery 1, battery 2. Our second loop is inside there. So let's actually start at the 6 volt, because now 6 volts in our good direction. So 6 volt minus plus, because you're going against it and it's coming in. So I2 times 12 ohms, following the current now. Uh, this is this battery is actually going with our battery, so this is also a plus 12 volt. Minus I3 times 6 ohms. That's a V, ohms, is equal to 0, because now you're back at the end of the loop. And then our third loop is our big one. So let's go 9 volts minus times I1 plus 12 volts minus I3 6 ohms is equal to 0. And now we're just going to do massive algebra. Matter of fact, I just want to plug and chug it into my calculator. Just one big thing. Your fourth and final equation that relates everything is that I1 is equal to I2 plus I3. Don't forget about this one. I tend to forget about it and then do it in my head and then get points off on the quiz. That's literally what happened on my last quiz. I just forgot to write that down, so every time I referred to this, it was in my brain. And all the rearranging and then changing the numbers to get different numbers, I did that in my brain. And then I didn't write it down. So I skipped a couple steps because I had that in my head. Make sure you write it down. You're going to lose massive points for that. Electrical measurement instruments. What I have to really understand for that is that you cannot. Um, what's a color to show this off with? Purple. You can't. You cannot run a voltmeter meter in series with a circuit. And this is just the dedicated voltmeters, like the ones we used in our labs, and thus for our intended purposes here. In this, you cannot run a voltmeter in series with a circuit, because voltmeters technically have infinite resistance or really, really high resistance. And amp meters are not to be run in parallel. And you could think about it for literally the exact same reason why I stated up here. Anything parallel is equal in voltage, anything in series is equal in current. And this applies to your amp and voltmeters when they're drawn in a circuit, or they tell you to draw a circuit that will measure the current in the circuit and the voltage across the circuit. That is exactly what they're asking for. That's going to be the trick question on the exam. I will dare you bet you on that. Okay. And then resistance and capacitor circuits. And because we really didn't go in depth to the differential equations, into how they work and how to figure out current at every single point of changing rate values of massive things, you're going to learn that in circuits one. Rest your soul. I hated it when I hated that portion of it. And you're going to have to do it with inductors too. But maybe we're going to have to do it next chapter. But right now, don't have to think about it. So RC circuits is honestly, this is the easy part because it's all conceptual and you're just measuring the if circuit at t is equal to 0, t is equal to infinity, and knowing the behavior, behavior of a circuit. Circuit. Knowing the behavior of the circuit between the 2 points. Okay? And the behavior between the circuit. Oh, by the way, this is for capacitor circuits. Capacitor. So, okay, let's give you an easy one. Okay, let's have a nice kind of. I'm actually just gonna pull up the discussion for this, not the discussion, the the cool. Yeah, I'm going to. I can't say this because it's going on YouTube. Uh, I'm going to pull up a question. Yeah, that's how I'm gonna go about it. A question. Okay, yeah. So, um, I'll be 100% honest. Batteries are just used to demonstrate, like, oh, if it's brighter, it means it has higher current, and if it's lower, it has lower current. If they substitute it for resistors, think about them the same way. You can actually, you can actually probably, if you understand that concept, you could look at a, excuse me, at a massive grid of resistors, and if thinking them as light bulbs make you feel better, or vice versa, do it. Because if that makes you understand better, then do it. Okay? So we have a battery with a resistor, hint, hint, wink, wink, resistor A, and then resistor B, and then a capacitor with a switch. Okay? This has a voltage of VBAT. Not bat, I can't say that. V1. This has a resistance of A, B, and then the capacitor is C. Okay, so uh, these these have the same resistance actually. So let's just say they're both 10 ohms. Is that a bug? Get off my laptop. Dead. Okay. Um, 10 ohms, and the capacitor is an unknown of capacitance, but we're just determining it based off of voltage right now, so it doesn't matter. Okay? So the circuit is at time zero. Actually, we don't even have to think about it. Circuit is open, the switch is open. How is the current going to flow? And if you think about it, this is open, so only current is going to be passing through that section. It's not even going to touch the capacitor. Now, time zero, at T0, switch close, 0, switch close, close. What would be the behavior of the current path? And the behavior of the current path would be that it will instantly treat the capacitor as if it's a short, which means it will not even touch our resistor B. Okay? Because current takes the path of least resistance. Now at T0 0 plus, which is just like just an infinitesimally small right after, a little bit of current's going to go through B. And I'm going to talk about the behavior of the capacitor right now. So between T0 plus to infinity minus, that's how we're going to define it, the current from the current going into C will be slowly decreasing because the capacitor is going to climb the voltage until it reaches the same voltage of V1. And that is the property of capacitors. So it will slowly get bigger and bigger and bigger while this one gets smaller and smaller and smaller. And until your path is back to uh, till your path is back to this inner loop, completely forgetting it. And then at t, that's what's going to happen at t infinity. Now here's the fun part. You, let's say there was also a bridge here with a switch. Like, now I'm going to change the circuit just a little bit. Um, no, I don't need a battery. With a switch, and there was also, let's assume there was also a switch in here. That was closed at the beginning. Now, let's say I close the switch, this switch, and open this switch. So This is switch 2, this is switch 1. So switch 1 now takes the battery voltage and our battery completely out of the system. And now voltage 2 completes the circuit, so it's still a closed circuit. What happens? This is the fun part. Now the capacitor is discharging and it will act as if it's V1. It would act as if it's V1 now. And then if they wanted to get the instantaneous, so T0 infinity plus 1, you will have to solve for the circuit as if this is a battery and nothing else changed. And then you could get the instantaneous current around the rest of the circuit. And I believe that covers everything. So I'll see you later. See ya later. I am so tired. I am going to be cooking for like 13 hours tomorrow or two on top of this and have a lab report. But I'm a good person, I swear. So, um, love you all. Hope this helps you. Good night.